Alright. What is the change? This airplane starts at rest at an airport runway at sea level. So I'm going to count sea level as 0 for gravitational potential. What's the change in mechanical energy of the plane if it climbs to a cruising altitude of this and maintains a constant speed of this? So right away they're telling me that there's work going on here. And notice the units they want are megajoules. So, alright, so I know there's going to be some kinetic energy going on there because the plane's moving. Am I going to have some potential energy due to grav? What do you guys think? Yes, because it's gaining altitude. So I'm going to do a column of PE grav. It's fancy and make that subscript. What about PE for spring? Any springs involved here? No. So I'm not going to even bother to label that column. I'll make a copy of this. There we go. Okay. So in my beginning situation, I'm at rest, so no kinetic energy. I'm at sea level, so no PE grav, because I'm going to call sea level 0. Then my engines kick in. So my engines do a whole bunch of work on me. Then afterwards, I'm moving fast. And I've gained a bunch of altitude, so I'm gonna say I'm there, and then we'll pick another interesting color for, and I've gained a bunch of PE grav. 0 plus 9 equals 5 plus 4. So, yay, energy's conserved. Does it matter which one we made higher at this point, KE or PD? What do you think? So the question was, does it matter which one we make higher at this point? No, it doesn't at all. Because we're different. The important part is that we're conserving energy. So that would be a full credit Y there. No words needed. And what I'm going to do now is use that as my starting point for my how. So right down here my how. And I'm going to start with the fact that what my graph just told me, that the work, which is what causes mechanical energy to change, is the kinetic energy at the end, which I'm going to call final, plus the PE grav at the end. So I'll call that final also. And that's right where I'll start. Be good to have some equations. Let's grab from my equation sheet. I need kinetic energy. Oh, there I got kinetic energy already in my thing. So here's my kinetic energy equation. And then I also need PE grav. Grab that from right down here at the bottom of the sheet. Alright. And so the work that's done on it is the change in the mechanical energy. So that's actually what I'm solving for. So now I can start substituting in. 1/2 m speed final squared plus m G, so the weight times the height final. I'm told the mass, let's see, I think it's here. 18, for me it's 1865. I'm told my final speed, 99.5. And that's in meters per second. Plus 1865 kilograms. I'm assuming this is happening on Earth, so 9.81 newtons per kilogram. And then my final height, I feel I'm going to run out of room as normal, 2,370 meters. And then just pull out the good old calculator. And I'm all in kilograms and meters and seconds and newtons, so I know I'm going to end up with joules. So let's see. And I end up with 4, 3, 5, 1, 7, 2, 2.75 joules. But they wanted it in megajoules. So mega is 6. 1, 2, 3, 4, 5, 6. So 43.4 megajoules. But all right, so I had a negative in there rather than times when I put mine into my calculator first. So I should have gotten W equals 5, 2, 6, 4, 8, 4, 2, 7.8 joules, which means the W equals 52.6 megajoules. It's amazing what happens when you put it in the right. All right, so number 5 here, we've got an apple falling from a tree, and they asked us to take ground level to be y equals 0. What they're using, at y equals 0, they're saying the potential energy, gravitational, will be 0. And they want us to figure out the kinetic energy, the gravitational potential energy, and the system energy when the apple is at 3.0 meters above the ground, so after it's fallen for a meter. All right. So we've got graph here. Let's add in some PE grav, right? Because we're going to have, we're going to have that because it's falling down. And I know I don't have that, but we know that there's no spring energy here because there's no springs mentioned. Yay. Alright. So now, at the beginning, the very beginning, it's dropped from rest. So how much kinetic energy does it have? It's dropped from rest. So here's the visual. I'm holding this. How much kinetic energy? None. Excellent. But a lot of PE grab, right? Because it's high, it's 4 meters above the ground. So I'm just going to go up here, give it a bunch. Then, there's no air resistance or anything that they talk about, so I'm guessing no external work. After it started falling, it speeds up. So when it's 3 meters down, it's going to be moving, but maybe not that fast, so I'm going to give it a low number there. And it's not quite on the ground, so I'm going to still have some potential energy gravitation because it's still above the ground level. And I was careful to make sure that the initial plus 0 equals my final, which I think it does. How many people had that for your Y? Nobody. Ooh, okay. What's one to work on then? I know it's a little tricky because it's not an absolute down, but... And just like last time, I'm going to start exactly at that point. So... my potential energy grab in the beginning, I'll call that initial. And there was no other energy going on there, no kinetic or anything. That has to equal my kinetic energy at the final position plus my PE grab at that final position. Grab my same two equations that I was using last time. I think I'll just go down here and grab them. Put them in here. I have them reserved. And now, let's see. So, the weight, my apple, times the height initial equals 1/2 the mass times the speed final plus the weight times the height final. Oh, there's a mass term in every one. What can I do? Get rid of it, right? So I don't even have to worry about it. So that, so no matter if it was an Apple or a Buick, it would do the same thing. So, now they want me to find out the kinetic energy, the gravitation potential energy of the system, and the PE grab and the total. So I need to kind of break up what I have here a little bit. Because I know this is true. Actually, I think I'm going to not cancel those out. There we go. So this is my E total. That's my total energy, right? Because that equals that. Here's my KE at this point. Here's my PE. grav that they want at this point. So really, now I need to figure out these individuals, right? Because they don't ask me something about the whole thing. So for my energy total, do some weird math notation here. The mass 0.24 whoops, 24 kilograms on Earth, 9.81 newtons per kilogram, and it's at a height of 4.0 meters. So my energy, wow, energy total equals, I get 9.42 joules. Oh, let's switch to my kinetic energy. So 1/2, 0.24, and do I know how fast it's moving there? Oh, I don't. So maybe I shouldn't do my kinetic energy next, because I still don't know what this is. So I can't quite solve that. Let's see. Let's try PE grav at this point. So PE grav final, which is at that 3, 0.24. This whole thing. 9.81 newtons per kilogram.
Why do you keep adding that in? The 9.81?
Because one of the rules of algebra is for each variable I need to put in its value. So M stands for mass, little g stands for gravitational field strength. So here I get 7.06 joules. Oh, that means if I did my energy total, minus my PE final would equal my KE final. So I get 2.35.
Do you plug that in with comments? Like answer?
Did I do what?
Like how would you?
Yeah, that's what I'm going to do. Because they asked for separated by commas. So they want the KE first, and they want 2 sig figs. So I'm going to put in 2.4, comma, then they want the PE grav, which is 7.1, and then the energy total, which is 9.4. Yay! Yeah, so separating by commas. which, because of rounding, notice that they don't add up. The 2.4 plus the 7.1 doesn't equal 9.4. So that's because of rounding. So. Yeah. All right, looking at number 7 here. We've got a pendulum named Bob. The mass of this is moving to the right at point B with this speed. The change in the gravitational potential energy when Bob reaches point A. What is the speed of Bob at point A? So I'm going to make the assumption that point A isn't the top of it. Because even if it is, if I assume that A is the top, then I'm assuming that it stops there. It may or may not be. If I assume that it isn't the top, then and solve it, then what I'm going to find is the speed, and if the speed ends up being 0, then I know it was the top, no harm done. All right? So I'm going to go under the assumption that A is not the top of the swing. So let's grab some. Again, I know it's shocking. We have PE grav. Grab the right one. All right, so where do we want to say gravitational potential energy is 0? At what point? I picked B. I agree with B. Because then, if I say, because the change between A and B is easy if B is 0. You know, you got change final minus initial. If initial 0, easier math. So I'm going to say this is at point B. The initial is B, so no PE grav. Some KE here. So I'm going to say it's got a bunch of kinetic energy. Just give myself some thing. I don't think there's any air resistance or anything. Air resistance is negligible, so that means no external work. So then at the top here, its KE is going to be lower, and its PE grav is going to have increased. Okay? Does everyone agree with that lot? I hope so, because it's right. I think it's right. Yeah, it looks right. I just know we're going to need that, so why not? So I'm going to start at that same point that I have been using my equation. Kinetic energy initial in this case equals kinetic energy. And rather than initial, I think I'm going to call that B. You know, I can label whatever I want. At B equals kinetic energy at A plus the potential energy gravitationally at A. And so I don't forget what I want. They tell me about the initial velocity. They want to know the gravitation, the change in it, which we know is going to be my gravitational potential energy up there, and what's the speed of Bob at A. I think I'm going to need to find the gravitational potential energy by itself. And I'm going to have to use a little bit of geometry here. Like, which group did the in-class problem with the pendulum? I think we're going to have to use the same geometry that you guys used on that one. So, if I've got here, and here, this is H, I call this Y. For me, that length is 1.2, so this is 1.2 meters. My angle is 35. And so I know that like Y plus H equals 1.2 meters. And Y equals 1.2 meters over cosine of 35 degrees. Because I have a right triangle in here, and I can use good old my friend SOHCAHTOA and a little bit of logic there to get that factor. So I would get that H equals 1.2 meters over cosine 35. I don't know what that extra little thing I'm getting in there is, but I have a feeling this is about to crash on me. Alright, so hopefully the board stops misbehaving now. Oh. So we can figure out H, which is the change in height of the pendulum bob, by that. Second most common mistake on this will be your calculator not being in degrees. Mine is. Thank you. I'm impressed. Me too. Julie, do you need to be plugged back in? Oh, and then you're wrong here. Oh, no. I made a mistake here. So we know cosine is adjacent over hypotenuse. So the adjacent side is going to be times cosine. So this is 1.2 meters. Cosine 35. Yeah, see, again, guys, make sure you use concepts we've actually used, and you'll find a lot more success. So that makes more sense. And I get 0.217017549 meters. So that's my change in height. And now I've completely and all that forgotten what we were looking for. Change in the potential energy and then speed. Alright, so let's do the change in potential energy first. So that's going to be most shortcuts only work on the exact same situation. So I get my TE G of A is 0.490 joules. And then I'm going to have to use that. I'm going to use this factor to find my velocity at A. So I'm substituting into that green, so 1/2 m velocity at B squared, or speed of B, 1/2 m speed at A squared, plus my answer here, 0.489656691 joules. And I know the M's, I know the VB, all I have to find is the VA. So it's just substitution after that.